Is it fine? Is it full screen?
Yes, full
Perfect.
screen.
Okay, so yes, I will start this day with a presentation on the Wavewatch 3 model and the generalities on waves, and also the coupling, a bit of information between the coupling between Wavewatch and CROCO. So first, some waves and C-state generalities. Here we have a sketch of different waves, processes and measurements. And it represents a lot of processes going from the open ocean to the coast. And we can see processes in the open ocean like mixing, wave breaking, and a lot of different processes, and remote sensing measurement of such processes from space. We can also see some interactions which are kind of represented with RC fluxes or with sea ice, for example. And this sketch also represents numerous interaction of waves when approaching the coast, notably with land and with the water column in the coastal zone. And also some measurements are focused here, also are seismometers, as waves can sign in such measurement in the Earth crust. So yes, waves are quite important for air-sea interaction, land-sea interaction, ocean-ice interaction, ocean crust interaction, and also important for some applications like engineering, offshore and littoral structures, and maritime transport. So what are waves? We think of waves as a general large crests that we see at the ocean surface, for example, here from the coast. But there are also a lot of short wavelets riding on these large waves, as can see in these two pictures. And so this collection of waves, which can be long, short, tall, small, are referenced as the sea state. So here is the schematic representation of all these different possible wave systems, so that are superimposed to create the full sea state. We can characterize the waves with different parameters. Notably, they can be characterized between the distance in between two crests, so this is the wavelength, or between the time between two crests passing a fixed point, this is the wave period. And usually we can represent the broad spectrum of waves in diagrams like this that are a function of the wave period or the wavelength. And we can see that we have a variety of different waves represented over there, like tide waves, long period waves, which comes from storms and earthquake, infragravity waves, which are large waves generated by interaction of smaller waves and shorter waves. So classical ordinary gravity waves, ultragravity waves, and capillary waves, all of these generated by the wind. So if we look at the spectrum, because waves are a lot characterized by their spectrum, as I said, a spectrum of the power spectra of the surface elevation here. It's a log scale, of course. So the evolution of the surface elevation show different region of the spectrum. So here we have infragravity waves at large time, large period. And then we have swell peaks, and here a wind sea region. And this spectrum is a distribution of the variance of waves across scales. So it is very used to characterize waves, and I will speak a lot about wave spectrum here. And so the full energy is characterized by the integral of this spectrum. Also, the significant wave height, which is used to characterize waves, is also accounting for the full spectrum, as it is defined as 4 times the square of the total energy of the spectrum. So The difficulty in modeling waves is that waves are characterized by really small and short time scales, around seconds or minutes, tops minutes for infragravity waves, and really small spatial scales. And we can want to have application as to wave climate at the global scale. So to be able to describe the sea state in such a large range of scales, we usually use the spectrum to define the sea state. A few last words on some generalities of waves. So yes, wave energy propagates at a given velocity given by the group velocity of waves and the background velocity, which is current velocity. And such propagation is different for each spectral component, so this is something to remind. Waves also turn. They follow geodesic and so grid circles during their propagation. Here is a representation of the propagation of wave around in the Pacific Ocean, for example. They also turn by changing the effective phase speed. This is refraction. This is pictures with the little schematic with C plus U dt change. Waves also show, so that is, it happens if the velocity Cg plus U converge, and it happens usually in coastal region, but also possibly when crossing current velocity gradients. So when this happens, energy density increases and the waves goes up in general. And steep waves also break. So this full variety of processes have to be modeled, as well as wave generation in a wave model. So modeling wave. As I said, waves are usually modeled using the spectrum, which is an average representation of the wave systems. And so spectral models such as Wavewatch 3 resolve the equation of evolution of the wave spectrum, which is represented over there. So a wave spectrum here is represented on the right, and we can see it's oriented toward the north, and the different radius represent different wavelengths, and we can see different wave systems in the spectrum. So at small wavelengths in the bottom right, we have the wind sea, and at larger wavelengths, we have different swell systems. And this is from the Wavewatch model, for example. So we have to solve the equation of evolution of the spectrum at each physical point of the model, which are represented there. So at each point, we have to solve the advection of the spectrum, for example. So the variable will depend on x, y, but also on the spectrum dimension, so that is the frequency and direction. The variable that is solved is the wave density or action in the spectrum. Actually, this variable denoted n here in the equation, it can be related to the energy. So why energy or action? Actually, action is a more general invariant than wave energy. For instance, in wave current interaction, there is an exchange of energy between the currents. And so we usually use the action which to describe the spectrum evolution, but there is a relation between action and energy that is given by this equation on the bottom. Some details about this equation, which is given first on the Eulerian view. It's actually solved in more Lagrangian point of view. And so there is it's an advection equation on one side and source term on the other side. And this equation is actually an hyperbolic equation which has a well-known solution method. So it can be solved with a numerical model. I'm going to talk a bit more about source terms. as actually they represent many different effects. For instance, generation of waves by the wind, nonlinear evolution of the wave, dissipation due to breaking or to bottom friction, and scattering and reflection of waves. So there are many source terms in Wavewatch. I won't detail each of them here, but I will talk about some of them. And these source terms need to be set up properly, and they use a lot of parametrization. So there are kind of important terms and kind of tricky to set up, but it's like that. And so one word about the accuracy of wave models. So it's obviously a function of choice of parameters, forcing parameters, which are winds, current, water level, sea ice, etc. A choice of parametrizations, and a choice of model numerics, like every model. Wave model validation is mainly done using HS from altimetry and in situ buoys when they're available. But there is something to remind that is that wave models are very well parameterized to provide good HS, but when going to the frequency spectrum or even the full 2D spectrum or source terms, there we are talking about aspects that are clearly less validated. So obviously wind errors are among the main source of error in wave models. So if you have a bad forcing, of course you have a bad wave solution. But this is something very important, and there were a lot of work done on wind input source terms in Wavewatch and in wave model in general. Currents are also important and can create large differences. They can have effect on very small scales, and wave height gradients, I will show a picture later, are probably dominated by currents. Here you have a little example of that. It's a representation of, in black, data from a buoy offshore Brittany. And it's HS, which is represented as a function of time. And in blue, you have the model with current, including current effects. In red, you have the model without current effect. And you can see that there are a lot of oscillations that are well reproduced when including current, and which are absolutely not reproduced without current. This is mostly due because we are offshore Brittany and there are strong tidal currents, so that are really important to model and to take into account. And as I said a bit earlier, source term parametrization tuning can be quite complex, but it's a really important step in wave modeling. So what do we have as output of wave models? As it solved the spectrum evolution, we can have full 2D spectra, so frequency direction spectra. We also can have 1D spectral data it's integrated over directions, EF, as a function of F, and we can have also bulk parameters, which are actually derived from the spectrum. This is the case of HS, which is the integral of the spectrum, or the average period, or stuff like that. Or they are also provided by the source terms like the wind stress and stuff like that. So the bulk parameters are usually output on the full grid, because it's only one value per grid point, so it's not very heavy. But spectral data are usually just output in dedicated point where you want to look at specific stuff, because there are kind of really heavier data. For example, the full spectra, it's a dependence on time, X, Y, frequency, and direction. So it's a big data. Some details about the numerics of Wavewatch. So Wavewatch solves the full density spectral evolution, not at once, but it split it into 3 parts. One part that solves the advection, one part that solves the refraction, and one part that solves the input by source terms. This is because the timescales involved in generation and propagation, for instance, are very different. And so it uses a time-step splitting algorithm to solve these three parts of the equation with different time steps. So when you're using Wavewatch, you have to set up 4 time steps, a global time step, which is the step over which everything is integrated in the end, a time step for advection, which is constrained by stability constant and CFL conditions, a time step for refraction and wave number advection, and a time step for source terms. So maybe some practical rules for choosing such time steps, because it can be a question when you want to run the model. So first, the global time step, it requires a relatively small factor between this time step and the advection time step, say 2, 3. In practice, it's used like that, as we don't want to propagate information over barely resolved bathymetry in one global time step. Then we have the DTX here, which is the advection time step. So this is just conditioned by the CFL criterion. We don't want that information can jump from over more than one grid box, one grid point. This is classical usual CFL criterion. And so I put here the little equation that can be used to compute this DTX, as it depends on your frequency discretization, and so on F-min, which is the minimum frequency used in your discretization. Usually it is about 3 or 4% of the X, but you have to compute it properly with this little formula. Then you have the refraction time step. Refraction includes, so as I said, grid circle direction changes, and depth and current refraction, and wave number shifts. So refraction is quite filtered in the model, so it's limited for stability. And when you reduce the refraction time step, you will reduce the use of the filter. So generally, you can keep a relatively larger time step, which is in general set up to half of the global time step. But you need to check if lower time step has no impact on the solution, and then eventually decrease your time step. And finally, we have the source term time step, which it actually represents the minimum used time step in the model. And it can really be used quite with a smaller value, and smaller DT don't result in the model to go slowly, but usually small DT for source terms results in smoother and faster models. So generally, the time step used for this source terms is between 1 and 10 seconds. Continuing on numerics, so Wavewatch have a lot of numerical and parametrization settings. So as Andres said yesterday, I think WARF has a lot too, but Wavewatch has a lot of parametrization. So you need to kind of appropriate the model to your use, and work a bit with it to understand the implication of all this parametrization and the setting of them. Here I just give a small tour of some settings that can be made, and this numerics and parametrization are actually chosen prior to compilation in Wavewatch using a switch file, similarly to what's done in CROCO using the CPP-Devs file actually. So this a tour of possible choices. You have choices about the propagation scheme, the generation and dissipation parametrization, the wave-wave interactions, the bottom friction, the CI treatment, the shoreline reflection, the interpolation method of the forcing fields, the use of coupling or not. This is something that I will come back to a bit later. The use of the NetDF4 library, the use of parallelization or not, etc., etc. So on the bottom, I've put an example of switch file. Actually, a switch file is just one line with these options set up inside, and it's used during compilation. Then there are still parameter adjustments that can be made, and this is made through name lists. So this is after compilation. When you want to use a model, you can set up a few parameters, as it's done in CROCO in, for instance. And this is done in a name list file that is named ww3grid.enp. And this is just a caption of what can be set up. So first there is a keyword for saying in which switch it will be applied. So for example, Pro3 is the propagation scheme of third order. And then there are some coefficients that can be set up. I've put also a few references for numerics and parametrization in Wavewatch 3 here, but there are a lot, and so you should refer to the manual of Wavewatch when you want to go a bit deeper on that. So in practice, Wavewatch to run, of course, Wavewatch, you need some grid. And there are several grid options in Wavewatch. So there are structured grids, which can be rectangular grids or curvilinear grids. Using these structured grids, there is a multi-grid option. So basically, you can do nesting with this multi-grid option. Here on the right, you have an example of a simulation that I've run with a global domain at ½ degree, South Pacific domain at ¼ degree, and multiple little domains around French Polynesia that are run at 5 km resolution. So basically you can do stuff like that. And you can see that the domains that I've plotted around French Polynesia are not squared, but they are still structured. It's just there is a masking procedure to avoid computing stuff where you don't need it. This was an open option for me. And there are also options to run Wavewatch with unstructured grids. So there is also an illustration. It's used for coastal and littoral dynamics, but it can also, unstructured grid can be quite complicated, and the numerics are quite different than from structured grids. You have to remember, there was a question, I think, yesterday about that for coupling, we can couple theoretically with both grids, but at the moment, in the distributed version of Wavewatch, coupling with unstructured grids is not set up. So, but I know people that made it work, so it can work, but at the moment it's not set up in the distributed version. To build these grids, Wavewatch requires 3 definitions: the bathymetry grid definition, the Lancy mask definition, and the obstruction grid. This is optional, the obstruction grid. It is made to account for energy decay due to subgrid blocking. So, for example, unresolved islands in your configuration. And to build these little files that are requested to build the grid, you can generally use reference data such as global bathymetry and global shoreline database. And there is a nice framework developed around Wavewatch, which is named GridGen, that can be used to merge these data and prepare files for Wavewatch trial running. Regarding the Wavewatch trial forcing, so water level, atmospheric currents, ice, and boundaries. For atmospheric current, water level, and ice forcings, there are 3 possibilities. First, they are not mandatory, so you can not use these forcings, but remember that with no atmospheric forcing, you won't have wave generation, and so you only have propagation from the boundaries or from existing waves. You can set these forcings as constant. It's an option. When you want to do some idealized experiment, it can be useful. And you can prescribe realistic fields from external files or from another model in the case of coupling. And all this is activated through different flags in the shell.enp file, which is kind of the name list of Wavewatch. For boundaries, you can run Wavewatch with closed or open boundaries. And so boundary data are only mandatory if you have open boundaries. And there are, at this moment, prescribed with from wave spectra. So you need wave spectra to prescribe boundaries. And this is performed by activating a specific mask value in the mask grid, which is the value 2 at the boundaries. And finally, initialization of the model. It can be set up from calm condition, so no waves, or it can be set up with a prescribed idealized spectrum at the beginning that can be eventually computed from your initial wind, for instance. And this is done with a dedicated program also. So I've put here the workflow of Wavewatch. So first you have the step of grid definition. So in light blue, you have the main programs, so grid, start, and shell. So first you have to set up the grid. You need some input files like bathymetry, obstruction, and masks. And also here, within the definition of the grid, it's a place where you have model settings like parametrizations. And then you have a file named moddef.ww3, which is the grid for Wavewatch in a binary file, and which will be used in all the other steps of the code. Then you have a start program, which is used to prepare initial conditions. And finally, you have the main program, which is the shell program, which is actually Wavewatch running. So the shell, in the shell, you need the grid definition binary file, previously output from grid. You need some settings within the shell.enp file. You need the restart file, which is output from initial condition program. And you have optional input like level, currents, wind, or ice if you use them. And as output, you will have a log file, of course. You will have eventually a restart file for next run. You can have output of spectrum for running another grid, if I defined one. And you have different output file. So the outgrid is actually the main output file with all the bulk parameters, so the average parameter on each grid point, like HS or the period or stuff like that. Outpoint is the file for spectral outputs, so just dedicated in some dedicated points. And track is a specific output for satellite comparison, for example. And yes, just to mention, there are also some utilities to prepare forcing files, boundary files, and to transform output files to netcdf or ASCII files. So there are just mentioned on the left here. So now just a few words about coupling. So why do we want to couple? Lionel has already said a lot of this stuff yesterday, but I wanted to point them again here in the context of really wave modeling. So waves are influenced by winds. Waves are also influenced by currents, water levels, and bottom roughness. And they are influenced by sea ice. In return, they feed back to a lot of fields. So the surface roughness is modified by waves and modifies the wind stress. The waves generate currents and modify the water level and the bottom roughness. The waves enhance upper ocean mixing. and the waves can break up the ice and push it around. And if all these feedbacks, and they do, have influence on waves, you need to couple. So here is a little sketch of a lot of coupled processes. I won't go into details in all of them, but it's a really nice sketch. And if you want to think about all processes, you should look at it carefully. I will just give an overview of some points in when coupling actually does really matter. So it matters when looking at coupled feedbacks through the wind stress. Indeed, drag coefficient is dependent on the sea state and dependent on the wave age. Here on the right of the slide, you have an illustration of the state of the art of drag coefficient parametrization existing in the literature, and you can see that there are a lot, and they are very different from each other. And especially at high winds, there are really a lot of discrepancies between this parametrization, which can come from in situ measurements, wave tank measurements, or parametrization set up from a theoretical hypothesis. And on the bottom, you can see an output of the drag coefficient as a function of wind speed from Wavewatch. So in gray, there are all what was modeled. And in color, you can see that it's a mean average depending on wave age. So you can see that there is clearly a dependence on the drag coefficient on wave age. So as we can see, we have this dependence for all wind speeds. So basically, coupled feedbacks of waves on the wind stress always matter. But we can see that it particularly matters when you have mixed seas, that is different wave age that induce a strong variability in your drag coefficient. There are also a lot of remaining uncertainties for high wind speed, as I said. And here the very different profile of drag coefficient are actually from hurricanes measurements. And so coupling is certainly important for extreme events. And finally, it's also important for coastal storm surge modeling, as wind stress can be really changing around the coast. So it matters for flux computation, and it can be quite complex. So here are two sketches just representing the flux computation and the different part of the fluxes used for wave generation, for wave to ocean energy flux, or from direct wind to ocean energy flux, or for boundaries. And on the bottom, you have also wave-ice interactions that come into the loop. So flux computation is not an easy part, but it's important. And in ocean atmosphere wave coupling, it's one of the biggest challenge. Then you have also feedbacks of the waves to mixing in the ocean, as I previously said. And here is an illustration from a recent paper by Xavier Couvlar, where he coupled the NIME ocean model to Wavewatch. And you can see on the right that you have for 2 seasons, the difference of the 1 meter depth turbulent kinetic energy between a coupled case and an uncoupled case with waves. So there is clearly a noticeable difference. And on the left, you have the impact of this wave coupling to the mixed layer depth distribution. And in black, you have Argo, like in situ data. And blue, you have the ocean-only case, so with no coupling with waves. And all the other colors are different level of coupling, with the red being the fully coupled model. And you can see that it's clearly closer to observation. Also, coupling between wave and current can be seen as very important in strong oceanic current gradients. Here on the left, you have a picture on the top of on the mean significant wave height gradient, so the difference in wave height especially, and under the mean gyroscopic current vorticity. And you can say that there is a very strong correlation between these two patterns. On the right, it's another illustration of this current wave interactions in the Agulhas region, with the vorticity on the right and the HS on the left, and you can see that here again the patterns are really really correlated. And finally, I've put back here the time series offshore Brittany, showing that accounting for tidal currents can be really improving the HS model solution too. And one last place where, of course, coupling matter is its nearshore dynamics, because in littoral regions there is a predominance of wave-induced circulation. And so there are many processes that are important to model, and I think that Rashid will give a better overview than me of these processes in the next talk or after. But you have importance of evolving water level, impact of current on wave evolution like refraction, etc. Wave-induced circulation, Stokes drift, acceleration by braking. You have enhanced mixing due to wave braking, surface and bottom streaming, mass flux due to wave rollers, and wave-induced pressure effects, wave-induced additional diffusivity, and wave-induced setup. So a lot of processes to account for. To go a bit more in the practical things. So here is again the schematic of the exchange field within Oasis in our framework. And I will just highlight here that for when coupling with Wavewatch, what we exchange is between Wavewatch and the atmosphere, we exchange the Charnock parameters and the winds. And between Wavewatch and CROCO, we exchange the currents and water level from CROCO to Wavewatch, and the average parameter, which are significant wave height, mean period, and mean direction from the wave to the ocean, as well as momentum flux from the wave to the ocean. So in practice, what you have to change when you use Wavewatch in coupled mode are these three little things. So first, in the switches, prior to compilation, you have to add the dedicated coupled switch with our Oasis and OASACM, as I say, nicely pronounce them. But they will allow the compilation in coupled mode with Oasis. And so the last switch, OA-ZOG or OA-ZAG, will be for coupling with ocean or with atmosphere, like the O and A change say. Also, remember that using Oasis, you need MPI, so you have to compile in with MPI and distributed switches. Then, once you have your Wavewatch compiled, you have to make some change to allow coupling in the shell.enp file, which is the name list for the shell main Wavewatch program. And there you have to activate couple flags for the forcing field. So if you want to couple, you put a C on the first flag, C like coupling, and you choose if you want to couple water levels, current, and winds. You can couple only one of them or separately, it depends on your configuration. Then at the end of the shell.inp file, you also have to define the coupling time step and the coupling field that will be exchanged. So here you have a time setting, and remember something important, the coupling time step must be equal to the global time step, DTG, that I mentioned earlier, which is defined in the grid inf. Otherwise, it won't work. So you have to be careful with that. So set up your coupling time step and your DTG at the same time and make them be the same. And then here you have some keyword in Wavewatch for coupled fields. So you have keywords for what fields will be sent. This is the first line under N, and keywords for the file, the fields that will be received. So you can find the detail about this keyword in the code or in the shell.in file commentary. Also, remember that you have, of course, to set up according to the chosen fields you want to couple in Wavewatch and CROCO the NAM couple file for Oasis. And prior to running your model, you need, of course, to prepare the grid of Wavewatch. And this has to be done sequentially, so not in MPI. And then you're ready to run, and so you will use the shell executable that will be launched at the same time with the CROCO executable through the MPI command, as you did yesterday for coupling WARF and CROCO. Here are just a few links and references that can be useful on this topic. So you have the link to the online documentation and to the online tutorial about coupling. It's quite more complete tutorial, so maybe you can go there if you want to work also on pre-processing and compiling and all this stuff about model in coupling. But today, in the afternoon, we will do a relatively classic tutorial just for coupling Wavewatch and CROCO. And then I want to highlight that there is in the CROCO tools, the coupling tools that you have used yesterday too, but they are really designed to help building couple configuration. There are a lot of scripts that can help you run this configuration. And then I just put some few papers that are really useful for when you want to couple Wavewatch and CROCO on the existing literature, but there are many others too. And this is it.
Thank you very much, Sven. Questions?
Yes, I have a question, please. Can you hear me?
Yes.
Okay. Please, can you repeat why Wavewatch use spectral model? I am not sure. Maybe by time special scales that the model can solve. I am not sure.
I'm not sure of what is your question. You ask why is Wavewatch a spectral model?
Why use spectral solution? Spectral solution? Maybe?
Yeah, Wavewatch actually, to solve waves, you have two options. Either you can solve the, sorry?
Yes, yes.
Either you can solve the evolution of the free surface. So this is what we want to do in the end. But if you have to solve each wave, so wave by wave modeling, so solving the full evolution of the free surface at each wave, you need a very, very high resolution, spatial resolution. You need to solve every wave crest and this. And this can be done in very small domain in the littoral region or something like that, in the nearshore region. But obviously, if you want to model waves at a global scale, for example, or even a relatively large regional scale, you cannot solve each wave. So the idea of spectral models is that they solve the evolution of the spectrum of wave, which is just a superposition of all the wave systems. And they use an equation of wave energy conservation to propagate and generate and dissipate this general spectrum. Is it clear?
Yes, more or less, but it's okay. Thank you.
Okay.
Any more questions on this? I have one question. I understand that the ROM's Rutgers code has also coupling for with Wavewatch and WRF. Do they use a different strategy, a different code for coupling?
Yeah, Rutgers has a coupling, but I guess it's not with Wavewatch, but it's with Swan, actually, which is another wave model, but quite similar to Wavewatch. And yeah, there is the COAST frame. I think you're mentioning the COAST framework, which is a coupling between WRF, Swan, and ROMS. And in this framework, it's the same strategy. It's the same kind of exchange parameters and stuff like that, but it's not performed using OASIS. It's performed using an embedded coupler within the model, so it's a bit less flexible. You cannot choose to use WRF or MesoNH, for example, or another wave model or things like that. But basically, the equation and the exchange variable behind are similar.
Okay.
I have other question, please.
Yes.
Do you know how many institute or research institute in general in Latin America use this kind of coupling model?
Absolutely not.
Okay, no problem.
I don't know. There are studies, but no, I cannot say to you. I cannot give you a number. Or...
Okay, thank you.
Well, I'm not. My ignorance is very big, but to the best of my extent, no one. I don't know of anyone doing forecasting, for example. No, not in forecasting, but yeah, coupling. There might be some studies, but I don't know. Maybe Brazil. Brazil has a lot of work these topics. I don't know if is correct here.
Yeah, I don't know. I would have to search a bit around. I know that there are people in Mexico that are using this framework because I've exchanged with them. But so far, I don't know more. And I think there are people in Colombia that wanted to go with coupling, but and probably they have been, but I don't know because so far I know they were working on ocean atmosphere coupling, but they were also working on wave coupling, so on wave models. So maybe they have coupled the models together. I don't know.
We are on the way. Sorry, I have a question.
Yes.
Good morning, Sven. You said that the wave are affected by the bottom ruggedness.
Yes.
But if I have a situation, a problem where I would like to know which is the effect of the kelp forest, for example, is possible to parameterize this effect?
I think it's possible, but I think you will have to go a bit deeper in the bottom friction parameterization, which clearly I don't know well in Wavewatch.
Okay.
But yes, I guess there is a possibility. I think that you have to prescribe some from roughness coefficients and stuff like that in the bottom friction parameterization. I know that we have that in coupled mode also you could set up the fact that that your bottom roughness could be provided, for example, from the ocean model, if you have it in the ocean model, because there is also question about bottom roughness for the ocean variables. But at the moment, we haven't had such exchanges in the model, and so if you want to do so, you should go in the bottom friction parameterization and set up some parameters.
Okay, thank you.
Perhaps this could be approached if you define a spatially variable bottom friction. Can you do that?
Yeah, this is always the question. We always dream to do that, but yes, in CROCO
okay.
we have done that. Now it's possible, but or it will be soon available. But in Wavewatch, I honestly I don't know how bottom. I guess that at the moment bottom friction, when you have a simple scheme, it's just a constant. But probably it is possible to provide a 2D field. But I think that, yeah, maybe it requires to add something in the bottom friction parameterization to input that. But I know that, for instance, for the reflection parameterization, you can provide a file of steepness of your coastline that is read and used in the reflection parameterization. So I don't see any technical issue to do the same for the bottom friction, but I'm not a specialist on the bottom friction parameterization.
Okay, thank you.
I see a question in the chat regarding the fact that yesterday Lionel said that HSL and TP were used to couple between waves and atmosphere. So actually, HSL and TP are provided from the wave model to the ocean to compute all the wave current interactions. And Charnock coefficient is provided to the atmospheric model to compute the effect of waves on the wind stress. There also exists in some parameterization in bulk formulation that use other variable of wave like HS or TP, for instance, to compute the wind stress. But at the moment, that's not what we have implemented, because it was not our first objective, but it can be performed too high. With a colleague, we are implementing a new parameterization for high winds that use the height of the wind sea, but it's not yet implemented.
Swen, I've got a question.
Yes.
Yeah, and regarding this, first of all, very nice presentation. And regarding this wave current interaction, I was wondering if this coupling and modifying somehow the distribution of this total energy, and I think it's in the near surface, and very likely, I think so, this will generate some kind of spatially variable flow, and then this maybe reflect some oceanic structures. And I was wondering in which scale this could be more noticeable. I don't know if you have some experience
I think it will depend actually on what you're looking at, for sure. You will have effects of wave current coupling clearly on the mixing, and so as I show on the mixed layer depth, for instance. So this is quite, I don't know how you want to define this scale, but it can be, at global scale, you have an effect on all the mixed layer depth distribution. And also you will have effects in really strong gradient regions, so where you have like western boundary currents and stuff like that. For sure you have differences in the wave field, and I'm pretty sure that you will have differences in the current and ocean tracer fields. And in the coastal area, the circulation is mainly driven by waves. So you have a total different circulation if you include waves or not. As if you have a high enough resolution, of course. We are talking about coastal, not, it's kind of the hundred of meters or between meters and hundred of meters resolution, not tens of kilometers.
Yes, I was thinking about, for instance, if you have this very nice example, like waves direction of winds, of course, propagating, opposing the local current, very likely you have this kind of variability on this total energy. And then I was thinking about maybe this total energy variability could be a proxy to study some kind of flow structure variability. You know, when you couple, you have this variability, and then this will likely reflect in this oceanic structure, and then you can correlate or associate with, I don't know, tides and this geostrophic flow, depends on where you are. I just, actually, it's not a question, it's just...
Yeah, but sure, you're completely right.
Yeah, maybe. Very nice presentation, Sven.
Thank you.
Okay, then let's take a break of 10